This section, 3.4, Addition and Subtraction Algorithms and Mental Estimation. What we're going to be working on this section is algorithms, and all loosely speaking that algorithm means is a way of doing things, a process for doing things. And the process we're going to do these things for is for adding and subtracting whole numbers. Remember, we're still working with whole numbers in this chapter. Some of these models are going to be, these algorithms, are going to be very applied towards young kids, and others are going to be more detailed and applied towards older kids, so you're going to see a little bit of both today. We're going to start with one that's going to be very applied toward younger kids, and this is a concrete model. This model that I'm going to show you has to do with what are called base 10 blocks. And you could also do this kind of a model if you wanted to with coins. It would work really well. I know that coins are really decimal values, but you can also do them for counting arguments, and that works okay. 34. The way that we would write 34 with base 10 blocks is the number 3 is in the tens place, and the tens are represented by units that are 10 long. And we call them longs. Okay, so this is a long. And I need 3 of them because it says 34. And then, since again the number's 34, I also need 4 more, but that's not completely a long because the long is 10 long. So I need 4 individual, what we call units. So here's 1, 2, 3, and 4. And of course, if you were working with the young children, you wouldn't draw these, right? You'd actually physically have blocks. And a very cool manipulative you can use that, well, let's say cool, but let's also be careful, is Legos. All right, so Legos work really well for this, actually, because they have the ability to connect. All right, so here's 34. My 4 units don't quite look like all the same. Pretend like they are for the moment. And then I'm supposed to have 18. So how many longs will I need for the number 18? 1 long. And how many units will I need? 8. All right, so concrete model, this is what I have. This works just great. And then what this does is it gives a very nice visual imagery for combining things in terms of place value. So if it's a long, it combines with another long, and we can count up all our longs. And if it's a unit, it combines with other units, and we count up all our units. But there is, in fact, sort of a problem inherent in what we're doing. So does anybody see what that problem is?
There's going to be more, like the 1 units will add up to a long.
Yeah.
Some extra.
How many units do I have here drawn right now?
12.
There's 12, correct? So imagine what you would do if you had those 12 little Legos getting there and you've told the kids that they can stick them together as long as there's 10 in a stack. Well, I can do that now, right? I can actually take 10 of those 12 and I can make them into a long. So if I take 10 of those 12, so here's 8, 9, 10. How many units am I going to have left over? 2. So here are my 2 units left over. How many longs am I going to have? 5, right? I have 4 up there already, and then I've circled in blue the other ones that I'm going to combine together to make a long. That's going to be my 5th one, so I'm going to end up with 5 longs. And then based on this picture, this model, what do I end up with? Like, how many is this? What is this number?
52.
Right, this is the number 52 because there are 5 longs and there are 2 units. This lends itself very nicely into what we are going to call our standard algorithm for addition. This is the one that you grow up knowing and probably feeling quite comfortable with, at least at this point. So here we're going to look at what we look like when we say, or what we mean when we say like normal. This is what my students were saying when they said like normal. Where do we start? The right side, yeah, which is a little bit counterintuitive because how do we read? Left to right. Already, we've got something that makes math a little different, correct? It's true. All right, so we start on the right-hand side. What do we get when we add 4 plus 8? 12. And so I do like this, right? No, why not? I got 12 and I wrote a 12 down. Okay, so instead of doing it like this, what we tell students to do is to do something called what? What do we call that? We usually call it carrying. Why in the world did I move a 1 over there? Because it represents 10. That's really important, right? The number 12 is 110, so that 1 went over into the tens column, and it has 2 1s left over in the ones column. And then what do we get? 4. 5, that sounds better. All right, so we have 5 in the tens column now, so here's 52. So that's the standard algorithm, and it has this idea of carrying involved in it. All right, what we're going to do next is we're going to look at an algorithm that takes this model and it expands it in a little bit different way, and it's called the expanded algorithm. All right, so the expanded algorithm looks like this. This is kind of a combination of the last 2 models a little bit. What we're going to do is we're going to take each of our numbers and we're going to write them by place value. So here's what I mean. The number 34 is actually 3 tens. So it's 3 times 10. Plus, it's 4 times 1. So we're just breaking it apart by place value. We've written this before. This is the expanded notation, right? We've done this in, which section was it, 3.1? I think it was 3.1. And we're going to do the same thing with 18. It's 1 times 10 plus 8 times 1. The nice thing about what we're about to do is that you can do this from left to right or right to left, and you'll see why in a minute. So I'm just going to go from left to right so that you can see it work, okay? So if I add 3 tens and 1 10 together, I actually have 4 tens. And all of a sudden, this feels like I'm working with $10 bills and $1 bills, doesn't it, a little bit? You've got that natural money sort of connection to it. And then how much do I get when I add the 4 and the 8 for the ones together? 12 ones. Now, I don't leave this as my answer. This is not 412. Obviously, we don't want 412 as our answer. That's probably not a good place to be. But what we do recognize then is that this can be broken apart exactly like you guys told me before. This is 110 and 2 ones. And I've got my 4 tens from before. So I have 4 tens. I have another 110. That is my total for my 5 tens plus my 2 ones for a simplified value, of course, of 52. All it really does is it expands that notation that we did when we carried. So do I recommend that every student do this every time? Well, obviously not. That's not my point. But the point is that when your students do not understand what carrying is, they're probably going to make a mistake doing it because they didn't know why they did it to begin with. And this can show you very well why you're doing it, right? You're actually turning that 12 into 110 and 2 ones. All right, the next one actually is called left to right. And it looks similar to what we've just been doing, but we don't have the base 10 notation, the times 10 stuff, okay? As we're doing this, and we're going to write it one number on top of the other one. So the very first thing I want you to do is to write down 1534 plus 3,218, like so. Okay, everybody good so far? All right, so I'm going to write the steps down that are, well, I'm going to write down what you would actually see on the paper, and then I'm going to write next to it why it worked, okay? So we're going to start with the left-hand side, the 1 and the 3. So if I take the 1 and the 3, what number am I going to get when I take 1 plus 3? 4. And it's in the 4,000s location, so I'm going to write down 4,000. Okay? We're going to do the same thing with the 5 and the 2. Sorry, mine don't even look like they're quite lining up very well. That was not good. What do I do when I add the 5 and the 2 together? 7 in the hundreds place. So this is 700. Now I've got the 3 and the 1. 4 in the tens place, so I'm going to write down the number 40. And then I've got the 4 and the 8. 12. And that's a single 12 at the end. Our last step is to add all of these values together. Basically what we've done is we've added them up by place value. We're going to add all of these together. We can move left to right or right to left on this one. Because of the way that these have been put in there, we won't have any carrying going on. Okay? So it works perfectly fine to continue this left to right business like we read. And then I can write down 4,700. I've got a 4 and a 1 together, so that's 5, 2. So 4,752. Now what's really going on? Well, what's really going on right here is that I got 4,000 because I took 1,000 plus 3,000, right? I added the thousands placed together. I got the 700 by taking 500 plus 200. I got the 40 because I did 30 plus 10. And I got the 12 because I did 4 plus 8. And this has the natural feel of moving left to right like we're teaching the kids to read. And so there is sort of a draw to do this because of that. Again, is it efficient? Do you know the difference between efficient and effective? What does efficient mean? Fast. It means you did it done quickly, right? Effective, what does that mean? It works. It's accurate, right? So is this efficient? Not very efficient. But is it effective? I think it's pretty effective. So for some kids, this might be what they need to see in order to be able to do this, at least for a time frame, to work up to being able to do this in a more efficient way, right? All right, this next one is a fun one, and we're going to come across this one again in the next. We're going to come across several of these again when we do multiplication and division. But this one is called the lattice algorithm. I quite like this one. I like it even more for multiplication. The lattice algorithm, we're going to write it on top of each other just like on the last one. Okay? In these, I think I used the same numbers. Maybe I didn't, but they're close. All right, so we've got 1, 8, 9, 4 plus 3, 2, 1, 8. And what you're going to do underneath this basically is draw a rectangle. Your rectangle is going to have 4 boxes because you have 4 place values. Okay? And then inside each rectangle, you're going to cut the rectangle in half along the diagonal that's the bottom left to the top right. And you have something that looks like a lattice. So that's why this is called this, lattice algorithm. Okay? Again, you can move from left to right or right to left in this algorithm. It doesn't make any difference. When we do multiplication, we're going to have several rows and several columns, and you can do any of them in any order. So for those outside of the box thinkers, we're going to do that, but inside the boxes, obviously. So, all right, so let's move from left to right just to make sure that you understand that that's totally cool. So when I add the 1 and the 3, what do I get? 4. Now, where do I write the 4? Well, I actually write it in the bottom corner underneath. So when I have a 1-digit number, it goes in the bottom right-hand corner. The next one, 8 plus 2, I get 10. So that one's actually a 2-digit number. The 10's digit is in the top corner, and the 1's digit is in the bottom corner. 9 plus 1, also 10. 1's digit is the 0, and the 10's digit in the top left-hand corner is the 1. 4 plus 8, that's 12, right? So the 1 in the top left corner and a 2 in the bottom right corner. Does everybody see where all the numbers came from to start with? All right, great. So now what we're going to do is we're going to add along the diagonals. All right, so let's do this. This actually also has the added bonus again of no carrying, just so you know. It doesn't really matter again if we start left to right or right to left. I'm going to start on the right-hand side this time. We've got the 2 going on over here. So we add 2 to nothing. It's just 2. In the middle here I have 1 plus 0, which gives me 1. And then the next one I've got 1 plus 0 again, which gives me 1. And I've got 1 plus 4, which gives me 5. And this is my answer.
Why do you get just 2 and then you get 5?
Why do I get 2 right here?
Yeah.
Because this column is only the number 2. Not column, but diagonal. The reason I get a 5 here is because it's 4 plus 1.
Oh,
I'm just adding between my yellow lines.
How you're going. Okay.
Yeah. And while it looks like that I'm somehow adding these things up here, I mean, I'm only looking at the lattice when I'm adding things together, only the values that are inside my boxes. And when I do multiplication, it really does matter that I start at the very end when I'm doing this addition stuff on the right-hand side. That's kind of why I started on the right-hand side here, because with multiplication, you do sometimes have carrying involved when you're adding multiple numbers together. All right, so the answer is 5112. This is actually fairly efficient. This is not that much more work in terms of numbers of steps or time involved than the standard algorithm that you know. And it does have this nice visual, sort of appealing to some kids. So we've got this one. All right, you ready for another one? All right, this one is one of my favorites. It's called Scratch algorithm. Scratch algorithm is not for use in every circumstance. So let's talk about when it's useful. The Scratch algorithm is useful when you're adding a lot of numbers together. So you'll notice this example, I didn't use 2 numbers to add together, right? I used 4. So this is a very good algorithm to use if you've got a bunch of long listed numbers to add together. Now, what we're going to do is the same thing as we did in the last ones. We're going to write them from top to bottom. So we're going to write down 34, 18, 69, and 87. With this method, we are going to start on the right-hand side. We need to do that with what we're doing here. But what we're going to do is we're going to add in such a way that we never end up having to add more than 1-digit numbers together. And that's the draw for this method. Because your kids are going to know, at least at some point, and when you get to 2nd grade, 3rd grade, they're going to know their addition tables for adding 1-digit numbers together. But they probably don't have committed to memory what 17 plus 6 is, right? That's where things go a little bit haywire sometimes, and then they start using their hands and things like that. Well, this gives them another option. All right, so here's what we do. We're going to start with the 4 plus 8. We're starting in the ones column on the top. 4 plus 8 is what? 12. This is like the 6th time we've done that one today, right? Keep getting the number 12. 4 plus 8 is 12. All right, anytime I get a number that's bigger than 10 or bigger, let me say it that way, then I'm going to scratch, okay? So we already got 12, so we're going to scratch out the 8. And here's what we're going to remember. We're going to remember the ones digit. So what is 4 plus 8? It's 12. What's the ones digit of 12? 2. So all you're going to remember right now is 2. You only can remember the ones digit. So basically, we've eliminated the 2-digit number that we really got, and we're only remembering the 1-digit number in the units place. Okay? That 2 now we're going to take and add to 9. What's 2 plus 9? 11. It's okay. We're all with you, Sydney. It's 11. Is that bigger than 9? I mean, is it a 2-digit number? Yes. So we're going to scratch. 11. What's the ones digit in 11? It's 1. So I'm only going to remember 1. And then I'm going to take that 1, and I'm going to add it to the 7, and I'm going to get 8. Is that a 2-digit number? No, so I'm not going to scratch. I'm simply going to write down the number 8. Now let's think through what we did. We scratched when? Whenever we got 10 or more, right? We scratched when we hit the number 10, basically. So every single one of those scratches, what are they worth? 10. Are you guys with me? That's what they're worth. How many times did I scratch? 2. So I have 2 10s. So my number that I carry over here is a 2. Let me slide that down just a little bit. I'm carrying a 2 because I eliminated be adding basically 20 to the value as I was working, right? I just made it easier to work with. And then we're going to do the same thing. What's 2 plus 3? 5, still a single-digit number. 5 plus 1 is 6, still a single-digit number. 6 plus 6 is 12. That's a 2-digit number, so what do I have to do? Scratch. And what will I remember? 2. I'm working with the 2. 2 plus 8 is 10, so I'm going to scratch. The ones digit in the number 10 is a 0. So I'm going to record the number 0, and I'm going to count my scratches. How many scratches did I make? 2. So what am I going to do? I'm going to carry a 2 over because those 2 scratches were actually worth the number 10 in the tens place, so 100, right? Yeah, so I'm actually have a 2 over here in the hundreds place now. There aren't any numbers in this particular problem in the hundreds place, so the 2 will just come down and be added, so this number is 208. It's really not that different than the addition that you've done. The thing that it eliminates is having to actually add a 2-digit number to a 1-digit number, and that usually results in kids counting on their hands. So it's actually more efficient, probably, than what you've done before. But it takes some practice. Okay? All right, we're going to do subtraction next. Concrete model. Remember what that looked like? Without turning back in your notes, what did it look like? Base 10 blocks. That's what we're going to do. All right, so we're going to do a concrete model. I think I already did 34 and 18, so I think I should just go back and get my base 10 blocks from my other screen. That way I don't have to do them again. Actually, let me change what I was about to do. Let me just do the 34. Okay, here's 34. And I'm supposed to be subtracting, right? And one of the models that we talked about in the last section, or it's actually section 3.2 about subtraction, is this idea of takeaway, right? It was one of the 4 or 5 models that we had for subtraction. And if we have 34 and I want to take away 18, concrete models, what does taking away the 1 in this number 18 mean? What does it mean to take away that 1 right there? That's a tens, which is what we call a long in base 10 blocks. So this is removing one of the longs. What does this 8 tell me that I'm supposed to be removing? What am I removing? 8 units, right? It's 8 of the little bitty blocks. And I got a problem. What's my problem? I only have 4 blocks. That's a problem. Agreed? So what do I have to do visually with these Lego blocks that I've all stuck together in order to actually remove 8? I have to take a long and I have to break it apart into the individual pieces, don't I? And that's exactly what we're going to do. So we've already taken away the 1 long. So we still have 2 longs left. So I've got 1 long here, and I'm going to take one of the longs and I'm going to break it up into individual units. And how many units is it going to become? 10. Okay, so it looks like it's longer than it was before because of the spacing. That's all that is, really. It's just spaced out. And then I still have the 4 original units that I had before, right? And how many am I supposed to remove of those unit blocks? 8. So we're going to go through and we're just going to eliminate 8 of them. So my answer ends up being how many longs? 1. How many unit blocks? 6. And so these are not equal steps. Please do not put equals in between them. These are different steps in my problem as I've removed things away. You know, one step is becoming the next step kind of thing, but they're not equal to each other. The last step, what is this value actually equal to in the last step? 16. 1 long, 6 units. Okay? So visually, you know, the first grader you're working with, the kindergartner you're working with, maybe the second grader who's got some difficulties with math, does this work for them? Yeah, as long as the numbers are small enough that we can use it with blocks, it works pretty well. All right, so we're going to do the standard algorithm next. Does this feel like we've done this already today? Just a little bit. We're going to write it on top of each other, 34 minus 18. Standard algorithm, where do we start? The right side. And we immediately see that we have a problem. What's my problem? You cannot take 8 away from 4. That's not okay, right? So what do we do in this algorithm? You borrow. You guys even used the right words. Very good. So how do we borrow? Amanda, tell me what I do next.
You take the 3 that's in the tens place and break it up into 2 tens, and then the 1 10 you add to the 4 and make it 14.
Okay, so all of a sudden now I actually have a 2-digit number in a 1-digit place. I really do, right? I have 14 in the 1-digit place here. So when I'm borrowing, why is it 14 again? I know we talked about this before. Why is it 14?
You add 10.
I added 10 because I borrowed something from the tens column, right? Didn't borrow 1, I borrowed 10 because that's what things are worth in that column. And again, this works really, really well, again, visually if you were dealing with money. $10 bills, $1 bills. What do you do if you have $34 and you owe somebody 18? Well, you're going to have to turn one of those 10s into 10 ones. We're ignoring the $5 bill for the moment. I get that, but just pretend. We're going to turn the 10 into 10 ones so that we're able to pay that money back. All right, and then we're going to actually have the ability to do 14 minus 8. So what is 14 minus 8? Somebody said it's 6. Good. And then 2 minus 1? 1. So we end up with 16. So what's after standard algorithm? Expanded algorithm. Yes, it is. All right, so we have our expanded algorithm. Again, it's going to look like these base 10 expanded notation. This is 3 times 10 plus 4 times 1. And I want to subtract 1 times 10, which that's okay. And I'm going to put the subtraction sign here just to remind yourself. We're also subtracting the 8 times 1, and that, of course, is the part that's not so okay. So physically, what we're going to see happen here is what Amanda was describing happening before, but we didn't really see it. We're going to take this 3 tens, and we're breaking it apart into 2 tens plus 10 ones, right? That's what we're really doing. We're breaking it apart into 2 tens and 10 ones. When I do that, I now have 10 ones and 4 ones. I still have the 2 tens at the beginning. 10 ones and 4 ones, which makes a total of 14 ones. And then I still have the subtraction of the 1 10 at the bottom and the 8 ones at the bottom. And then once it's in this form, I actually could add or subtract from either direction. We'll start with the right-hand side since we're modeling the standard algorithm here. I have 14 minus 8, 14 ones minus 8 ones, which gives me 6 ones. And this is, I mean, there's 6. It's a positive number. And then I have 2 tens minus 1 10, which gives me 1 10. And this, in a condensed form, is the number, of course, 16. Any questions about that one? Okay, the next one's my favorite. Are you ready? I like this one. Equal additions. Here's what I want you to write down next to equal additions. I'll write it on my screen too. It's that important. The goal here is to have no borrowing. If at some point in the problem you are still borrowing, then you did not finish the equal additions in the right way. Okay? All right, so we're going to write the numbers down just like we did in the other problems. 834 minus 158. And we're going to notice, just like we did, of course, in the last problem, that I can't take 8 away from 4. Everybody good? Okay. Our goal is to change the 8 into a number that's very easy to subtract and smaller than the number above it. In particular, it'd be really nice if it was a 0. Wouldn't you love to subtract zeros? It's easy, right? So how do we do that? Well, we do that by adding 2 to this number. But if I add 2 to this number, I have to add 2 to the number above it as well. So imagine, I don't know who's here, so come stand up here next to me, Jessica. All right, we're not quite the same height, right? We're close, but we're not quite the same height. So if I came into class one day and I had on 2-inch heels, which is going to put me about right here, all right, then it looks like I'm taller than Jessica, right? I can't just add 2 inches to me and say all of a sudden I'm actually really taller than Jessica, correct? But if I put on 2-inch heels and then you put on 2-inch heels, come on, stand up, then we're still the same difference in height, correct? That's all I did on the problem. Thank you so much. Is that I added 2 to both of the particular numbers. And as long as I add the same value, then I haven't actually changed how far apart they are. Make sense? Okay, let's actually add the 2 and then see what happens. So this becomes 836. This one becomes what? 158 plus 2 is 160. Fabulous. So can I do 6 minus 0 now? Yes, I can. But then I've got another problem. What's the next problem? What do you see, Rachel?
Take
Yeah, this is the tens place, right? I can't take the 6 away from the 3. So what am I going to do? I'm going to add this. I'm going to add just like last time, but what am I going to add this time? What do I have to add to 6 to get it to become a 0, basically? 4. And it's in the tens place, so I'm going to actually add the number 40. All right, so what happens when I take 836 and I add 40? 876. Very good. And how about the 160 and I add 40? 200. Can I subtract this one now without borrowing? Yes, I can. And again, if I've made them zeros, which is the most appropriate thing to do, then they subtract easily, which was kind of the goal. This is 576. I didn't mean 500. I was just checking. Maybe not a 500. I was just going to keep the extra 100. That's okay. If you want 676, we'll go with 676. Okay, so the whole goal of this particular method is what? No borrowing. So if at any point when I ask a problem like this you find yourself borrowing, you did not actually complete the whole point, right? Even if you completed it for the ones place, if you don't complete it for every place, then we've got problems. One of the things that I like about this method is because this is exactly what I think when I do something like subtracting 18 or 19 from something. I don't really do it that way. I don't subtract 18s and 19s, not in my head, right? I subtract 20 and then I do something to make up for what I didn't really subtract, or I subtracted too much from it or something like that. So this is really good for mental addition, especially if it is just a 1-digit where you're changing something. This one was a 2-digit where you're changing something. I get that. But this is a really good idea for mental exercise. All right, we're about to change gears slightly. Any questions so far? Okay, we've done some things in it was actually section 1 of chapter 3 with other bases. Do you remember that? We looked at converting things between base 8 and base 10, base 2 and base 10, base 8 and base 12. And I mean, we moved in and among different bases, right? We also did from base 10 into other bases. So we did things with, we called it the division scaffolding, remember? And then the other one where we multiplied by place value out to go the other direction. Well, what we're going to do next is we're going to do addition and subtraction, excuse me, in other bases. In particular, whatever base it is that we want to work in, it's going to work the same way, but what you have to remember is what the place value, or what the numeral values are in that place value system. Base 8. Remember that base 8 has the digits 0 through 7. There are no 8s, right? If we get 8, we have a number that's not in that place value system. It's kind of like when we get the number 10 or 12 or 13 or whatever in our base system. I can't write, like I tried to in that first example, the 12 right in the ones column. I can't do that. I don't have a single digit 12. I have to do something different. And we're going to see that happen again here too. What I want to do is I want to show you what it looks like in our standard method, the one that you're most probably comfortable with, and then what it looks like in some other method as well, okay? So that I can give you some experience and some practice at using that other method with another base system. All right, so the first one is 3-4 base 8 and 1-7 base 8. So let's do it in our standard algorithm first. All right, so if I work in our standard algorithm, I start with the ones column, correct? And if I add 4 plus 7 together, what value do I actually get? Just in our base 10 system, what number am I getting? I'm getting 11. And of course, there's no 11 in base 10, and there's certainly no 11 in base 8, correct? So I should be getting this number 11. But what I want to think about is how many is that in base 8? In other words, how many 8s is that? And how many 1s is that? So in the number 8, how many 8s is the number 11? I mean, how many are in there? There's 1 8. And how many left over? 3. We're going to carry over 1 8, because this is the 8's place now. This is not the 10's column. This is the 8's column. I'm carrying over the 1 8. And now I'm going to say 7 plus 4 is left over is the 3. So I'm writing my 3 down. Does that feel a little awkward? It should feel a little awkward. I mean, really, it should. We're going to do the same thing now. I have 1 plus 3 plus 1, which is...
Could you explain where you got the 3 from?
Yes. Down here, I'm breaking this number 11 apart into a group of 8 and what's left over. So I had one group of 8, and then I had 3 left over that didn't get into that group of 8. So the 3 is remaining in the 1s column, and the 1, 8 is being carried over to the 8s column. Yeah. All right, 1, 3, and 1 is 5. Do I have a 5 in base 8? Yes, I do. So I get to write 5 down. I don't have to do any carrying or anything like that. I have 5, 3, base 8. Please remember to write down that subscript. So let's do this. This will be our last one with scratch addition. I know that scratch addition is not necessarily useful in the sense that there aren't multiple numbers, but it'll still work here, and so we're going to give it a try. All right, so when I add 4 plus 7 together, just like we just did before, it's 11, correct? And that's too big because it's bigger than 8. Good. Actually, it's bigger than 7, right? It's bigger than the biggest digit I have. It's 8 or bigger. So the fact that it's 8 or bigger tells me, just like in our system, because it was 10 or bigger, I scratch. And the question is, how much bigger than 8 is 11? And the answer is 3. It's how much bigger is it? So when we did it in our place system, we got the number 14. We really were saying, how much bigger is it than 10? And we said, oh, it's 4, so I'm going to remember 4, and then I'm going to keep going, right? Well, here, the number 11 is 3 bigger than 8, so that's the number I'm going to write down. And then again, I look at the 1s column, and I ask myself, how many times did I scratch? Obviously, just once here. So I carry that 1 from that 1 scratch over. And then I have 1 plus 3 plus 1, which is 5. So we end up with a 5 in the 8s column, and this is 5, 3, base 8. All right, so we'll stop there today.